This is part 1 from chapter 10 in Chemistry 2E on liquid solids and intermolecular forces. Here we have a picture of solid carbon dioxide, which is also called dry ice, and when it's placed into test tubes or graduated cylinders with some water in them, it sublimes vigorously, going from a solid directly to a gas and carrying out some of the water vapor with it and forming a fog. In fact, this is what's used in movies and on stage to create that fog effect. Topics for this video: solids, liquids, and gases, some molecular comparison, and secondly, intermolecular forces, called IMF, forces that hold condensed states together. We'll start off by comparing 3 states of matter. We can see here we have steam at 100 degrees centigrade, really low density, pretty large molar volume, and we can see the view of the water molecules, a lot of space between them. Liquid water at 20 degrees centigrade has a much greater density. Notice it isn't 1. In order to have a density of 1, it has to be really at 4 degrees centigrade. And that's its volume, and the molecules are a lot closer together. And then in ice at 0 degrees centigrade, we have a density that's a little bit smaller than the liquid. And that's one of the reasons why ice floats. And a little bit larger volume. And the volume is due to having space between the water molecules that we don't see in the liquid state. And that space is due to hydrogen bonding, pushing those water molecules further apart. And this chart just goes through some of the physical properties of water when you compare the solid, liquid, and gas states. Low density for gases, liquid and solids much higher. Shape, indefinite means not constant. So a gas and a liquid take the shape of the container, where a solid has its own constant shape. As far as volume goes, a gas has no definite volume at all. As you know from studying gases, gas volume changes with temperature and pressure. A liquid, though, has a definite volume, and you can measure that volume. And this is the last thing we want to look at over here, because that's what this whole video is really about: the strength of the intermolecular forces and how the different properties that we see, like boiling points and melting points, really derive from that. Now for gases, particles have complete freedom of motion, constantly flying around, bumping into each other in the container. And there's a large amount of space between the particles compared to the size of the particles themselves. And we can see here with this piston cylinder setup, a lot of space between these particles represented by the green balls. And you can see you can push down on that piston. That means you're increasing the pressure on it and force those gas molecules together, so a gas is compressible. Liquids, on the other hand, particles are much more closely packed together, but they still can move around each other. It's incompressible. As we can see here, there just isn't any space left to push those particles closer together. And liquid takes the shape of the container and they flow. And we'll be checking out flowing later on. They can't escape or expand to fill the container like a gas does. Now for solids, we're going to put solids in a couple of different categories: crystalline and amorphous. Solids, particles are packed close together in fixed positions, and they vibrate. Now it says may vibrate. As the temperature is lower, they vibrate less and really stop vibrating at absolute zero. Solids, like liquids, are incompressible. They retain the shape and the volume. Now checking out crystalline versus amorphous. Crystalline solids, the particles are arranged in orderly geometric pattern, and the example is salt and diamonds, and we can see it up here. And these particles are small, so they can be on the order of small molecules or ions or maybe even atoms. But as molecules get larger and larger, they lack that ability to line up very well, and you wind up with this amorphous state, which really means without shape. And one big difference is that a crystalline solid will have a well-defined melting point and boiling point, whereas an amorphous solid will not have a well-defined melting point. In fact, it melts over a range of temperatures. And you can see here under amorphous solids, examples will be plastics and glasses. Now wax is another example of an amorphous solid. We're going to be looking at phase changes later on as well. And the phase changes, if we start over here with the solid state, if we add heat to the solid state, molecules will vibrate more and more until they can finally start to break away from each other, and that's when it's melting. That takes heat to do that. Now we're in the liquid state here, and there's no order anymore once we hit the liquid state. And then if we heat it some more or reduce the pressure, we'll wind up changing into the gas state. And if we want to reverse and go from the gas to the liquid, we can do the opposite. We can cool it or just increase the pressure. We're going to see the effect of this later on as well. And then once we have the liquid state, we can cool that some more and change it to the solid. You notice there's no change of pressure here because particles are already as close together as they're going to get. Types of intermolecular attractive forces. Now these are all called van der Waals forces or London forces. And we're going to go over 3 or 4 main types. One type is called dispersion forces, and they're a temporary polarity in the molecules due to an unequal electron distribution. And you're going to see that coming up very quickly. Next we have dipole-dipole attractions, permanent polarity in the molecules due to their structure. A dipole is another name for a polar molecule. In hydrogen bonding, an especially strong dipole-dipole attraction results when hydrogen is attached to an extremely electronegative atom, such as oxygen, nitrogen, or fluorine. Well, let's start off taking a look at the dispersion force. So we start here on the left with frame number 1, and this is really a helium atom. We have our electrons, spinning in their own orbitals. And we go from frame number 2, the electrons, constant motion. Notice they're opposite each other right here. But in frame number 3, they're on the same side. And what that does, by them being on the same side, they give this side of the atom a partial negative charge. And you should recognize that as the Greek symbol, lowercase delta, meaning partial. So this side of the atom becomes negative, and then this side becomes positive. So this is now a dipole, because now it has oppositely charged ends. And when that happens, you can see one dipole of helium can cause another dipole of helium to form. So the positive end of this helium atom influences the helium atom very close to it, and that those electrons are pulled towards it. So this end becomes partially negative, and then we have a third one happening. And just as quickly as these dipoles form, they can disappear because those electrons are in constant motion. It's almost like flicking a light switch on and off. Now let's check out the effect of molecular size on these dispersion forces. The noble gases are all nonpolar atomic elements. The stronger the attractive forces among the molecules or atoms, the higher the boiling point will be. And we can see that over here. As we go down the column for the noble gases, the molar mass increases, the number of electrons and protons increases, and so does the boiling point. So that means as we're going down the column, those dispersion forces are getting greater. So when we see the boiling points increases, that means the forces of dispersion are increasing as well. Because when you are boiling a liquid, you are trying to overcome those attractive forces. Now sometimes a molecular shape can cause a difference in dispersion forces. So let's check out these 2 isomers of pentane. Now N means normal pentane, and normal pentane is looked at as a straight chain. Pentane tells you there's 5 carbon atoms in the chain. Now we can also rearrange these atoms to form neopentane, which looks like 1 carbon atom in the middle, and then we're surrounded by these 4, they're called methyl groups, each one containing a carbon atom. Now if you were to come up with the formulas for both of these, they'd be exactly the same, C5H12. Now let's see what the difference is though of the shape. Now for the normal pentane, we have a straight chain. We have a larger area for interaction between one normal pentane molecule and another. Larger area for interaction means more places for dispersion forces to form. Whereas over here, in neopentane, because it's kind of a circular molecule, we have very little area for interaction. So this should have a lower dispersion attraction as we would than over here. So we would expect, if this was the only difference, that the larger this dispersion force would be for neopentane. Therefore, it should have a slightly higher boiling point than, for N-pentane, it should have a slightly higher boiling point than neopentane. And this would be called the branch chain, just so you know. Okay. So the straight chain isomers have more surface-to-surface contact. So chain isomers have stronger IMFs than spherical isomers. And this is our chain isomer here. Now let's check out the boiling points of the normal alkanes. So we have pentane that we already talked about a moment ago, that's going to be C5, and then we see C6 for hexane, heptane is 7, then we go octane is 8, nonane is 9. So the molecules are getting longer and heavier as we go up our graph. And if you look over here at the boiling points, just as we would expect, boiling point is increasing as well. And so that increase in boiling point can be explained this way. As the size of molecules increases, so do the dispersion forces, and thus the boiling points increase. So if you were given a question like this, where you had different formulas and you were asked which one of these molecules has the strongest dispersion forces, or IMFs, you would say nonane. If you were asked to arrange these in order of increasing dispersion force, you would put pentane first and end with nonane. Dipole-dipole interaction is an interaction between two polar molecules. We can see here we have a polar molecule, positive negative end, partial positive, over here, partial negative end here, and here's another polar molecule, or dipole, and see how the partial positive side is attracted to the partial negative side. Now the difference here is that these charges are always there, they don't appear and then disappear. Now let's compare a polar molecule with a nonpolar one where the molar masses are just about the same. So these were the structural formulas. Now look at the difference in the boiling points and the melting points. Formaldehyde, much higher melting point than ethane, negative 19.5 to negative 88. So dipole-dipole attractions are stronger than dispersion forces if molecules are the same size. Now we're going to check out dipole moment and boiling point. Now dipole moment is a way to measure the strength of the partial charges on a polar molecule. So remember, polar molecules are also called dipoles. And there is a way to measure how strong those forces of attraction are, and that's called a dipole moment. Now I'm not going to ask you to calculate that. I'm not even going to go through the formulas because it's not really necessary for what we're going over. Now let's check out our graph here. We have 5 molecules, and as we go up the scale, you can see the dipole moment is increasing, and as the dipole moment increases, so does the boiling point. So that means the molecules are becoming more polar as we go up to the right. So for dipoles, the more polar the molecule, the higher the boiling point, as long as the molar mass is the same. So you could be given a question where they ask you which molecule has the higher boiling point, and they all have pretty much the same molar mass, and the difference would be in the dipole moments. So that's what you have to note. Higher the dipole moment, higher the boiling point. Now let's check out hydrogen bonding. You may have covered this already in Chem 1. When a small, very electronegative atom is bonded to hydrogen, it strongly pulls the bonding electrons towards it. So here's some examples: oxygen to hydrogen, nitrogen to hydrogen, or fluorine to hydrogen. So these 3 elements have very high electronegativities. Because hydrogen has no other electrons, when its electron is pulled away, the nucleus becomes de-shielded, exposing the hydrogen proton. The exposed proton acts as a very strong center of positive charge, attracting all the electron clouds from neighboring atoms, as we can see here. So when hydrogen bonds directly to fluorine, oxygen, or nitrogen, the bonding atoms acquire relatively large partial charges, giving rise to strong dipole-dipole attractions between neighboring molecules. So these molecules here, although they look the same in our drawing, could be any of these. And you see how it's always negative to positive, negative to positive. So the stronger these attractions are, and that's due to really the electronegativity differences. The stronger those attractions are, the higher the melting points are going to be, melting points and boiling points. Now we're going to compare hydrogen bonding in water and ethanol. So here's hydrogen bonding in water, represented by these dotted lines. Notice the hydrogen bond is between water molecules, not within. Also notice down here that one water molecule can form more than one hydrogen bond. If we compare that to ethanol, ethanol, because of its structure, has an OH group on it, which is similar to the OH in water. So that little OH group itself can become partially negative and partially positive, whereas this other part of the molecule pretty much stays nonpolar. So there can be hydrogen bonding between ethanol molecules, and this little group forms the hydrogen bond. And if you add ethanol to water, you can also have water molecules bonding, forming hydrogen bonds to ethyl alcohol molecules. So what do you think the effect of hydrogen bonding on boiling point would be? Well, we would expect it to increase the boiling point. And that's exactly what we see here. Comparing ethanol to dimethyl ether, they both have the same formulas, they have the same molar masses, but there's a different structure. Now, because we have that OH group on the end here in ethanol, we have hydrogen bonding between ethanol molecules, but no hydrogen bonding here, even though that's a polar molecule. Now look at the difference in the boiling point. 78 degrees above zero, that's minus 22 degrees. So room temperature, ethanol is a liquid, but dimethyl ether is a gas. The last one I'm going to take a look at is an ion dipole force. A good example of that will be water and like table salt. Ions from an ionic compound are attracted to the dipole of polar molecules. The strength of the ion dipole attraction is one of the main factors that determines the solubility of ionic compounds in water. Here's a good example. So we add salt to water, and what happens is that the water molecules pull those ions away from each other, and then they surround them and bond to them. And notice that the hydrogen end of the water molecules here have oriented themselves towards the negative chloride ion, and then the opposite has happened here with the sodium. And this actually shields the sodium and the chloride from coming back together and linking back up, because they're still attracted to each other, but the water is stopping them from coming together. We're going to see this much later when we cover, in fact, in the next chapter when we cover solutions. Now, immiscible liquids are liquids that don't mix with each other. So we're starting off with pentane, which is a nonpolar molecule. Water is a polar molecule. The attractive forces among the water molecules are much stronger than the attractions for the pentane molecules. The result is that the liquids are immiscible. So here we have the pentane on top and the water on the bottom, just due to density differences. And you would see this demarcation or interface between the two liquids. So this is the pentane up here, and here's the water here, and this is the interface. You can shake this up all day, and they would just simply separate because the water molecules are more strongly attracted to each other. There's no real repulsion here. It's only about attraction. So the attraction between the water and the pentane is so small, there's very little mixing. Right at the interface, there might be a little bit. Right there, and that's pretty much it. This is similar to oil and water or oil and vinegar, like Italian salad dressing. Now, in summary, here are 4 different forces that we looked at in this video. You have dispersion forces, dipole-dipole, hydrogen bonding, and ion dipole. And you can see over here for strength, dispersion are the weakest, ion dipole are the strongest, and that bears it out with these values. Now these values, these numbers refer to the amount of energy it takes to actually separate 1 mole of these molecules from each other. So dispersion forces are instantaneous dipoles, but they come and they go pretty quickly. Polar molecules, the forces are the charges are there all the time, but they vary in how strong they are. So the stronger they are, then the more energy it would take to separate them. So dipole-dipole, stronger than dispersion if the molecule's size is the same. Hydrogen bonding, only between molecules that have these 3 elements in them. Now, ion dipole, again, ions bonding to a polar liquid like water. And there's very few polar liquids. Now this is the last slide here. See if you can answer these two questions. What intermolecular attractive forces do each of these have? And which substance has the strongest forces overall? Now when you look, you have water and candle wax. And so here's just a picture of them. And I'm telling you that water is polar, so water is a dipole, and candle wax is made up of nonpolar molecules. Melting points, boiling points for both. So why don't you pause the video and answer the question, which one of these substances has the stronger overall intermolecular forces? Okay, and the answer is candle wax. So the water has dispersion and hydrogen bonding, and the candle wax only dispersion. Now you might have thought then water should be the answer because it has two different types of intermolecular attractive forces. But what we really do is go by the properties. So the higher the boiling point and the melting point, the stronger those forces must be. Because when you're boiling it especially, you're separating one molecule from another molecule. All right, that is the end of this first video.